Hello, my name's Richard and welcome to this demonstration of how to solve locking and blocking problems using the Opsian profiler. In this demo we're going to have two different services. My main service, which is a kind of new system here, which in this demo scenario we've developed, which is a drop wizard based system. And in the background, I'm going to start up this legacy bank service. And the idea of this example scenario is that we're migrating the bank balances of some of our existing customers from the legacy bank service over to our new bank service. And in fact, we have a merge account script that's just going to repeatedly hit an HTTP endpoint in order to do the account merging, and we're going to hit it with several different customer IDs. If I just run that merge accounts benchmark here, it'll print out the total amount of time taken. I'm not going to make you wait here, so we're going to skip the video ahead and we'll see what the resulting time is. Okay, so that took about 28 seconds. If we flip over here to our profiling view, we can see that our little demo application has popped up in the Opsian UI. And we're going to take a look at some of the profiling data and see what's happened during that time period. Now initially, if we just looked at our regular profiling view, nothing in particular would jump out at us. And that's because we have got here a couple of different types of times that we can capture with the Opsian profiler. One of them is CPU time, and one of them is wall clock time. So the difference there is CPU time is measuring the bottleneck when your system is actually on CPU, executing instructions, and wall clock time includes the total time beginning to end of what your system is doing. So if we look at that filtered view, we can see along this side here the time taken to run our actual code. So I'm just going to narrow down to code in the drop wizard thread pool. And we can see that our bank account resource has got its merge accounts method being called about 11% of the time. And then our merge balance from legacy bank account method is called there. So this is where our bottleneck is really lying in terms of what our system is doing. And within that, we've got a method here called the legacy bank proxy.getBankBalance, which is taking 4% of the time, but there's a bit of a gap between that and 11%. So when you see flame graphs like this, where the parent box narrows in down to the child box quite a lot, those are situations where there's a lot of self-time within the parent box's method. Okay, so let's take a look at what that code looks like in terms of our system. Merge balance from legacy bank account method. We can see that we've got a method to look at the balance of the customer in question from the legacy bank account, and we can kind of deposit the amount in the customer's account and then persist that customer value back into the system. But actually, we can also see that we've got that whole method is synchronized on this transfer lock here. And the transfer lock is a single global lock for our entire system. That will be a problem because that means that all of our different threads that are running get serialized to one point when we're doing this update operation. Now, conveniently, I've got a get lock method for a given person, which just looks up a lock object associated with that person's ID. And that would enable us to have a different lock per person, per user, rather than one big global lock, a much more fine-grained locking strategy. There are different strategies you could use for locking here. I mean, you could use things like stripe locks, all sorts of things, but this is a nice simple. So if I restart that demo application, that's going to recompile our code and deploy it here, and we can rerun the benchmark script on the newly deployed system. Now, the last time we ran this, it was 28 seconds. Let's see how long it takes this time round. Down to 15 seconds. That is much improved compared with where we were last time. We don't just want to deal with it at 15 seconds. Let's see if we can speed this up a little bit further. I'm going to, again, look at that wall clock profiling point of view and look at the new flame graph for our system. So what is it doing now? Well, if we see what our legacy bank account is doing, we've clearly solved the locking and blocking problem because our bank merge balance from legacy bank account method is not spending lots of self time. It's spending all its time calling legacy bank proxy.getBalance. And we can see here as well, there's another legacy bank proxy.getBalance method. And that's dominating our execution time within this request. But if we look at what that get bank balance method is doing, it's not really spending much time internally. It's spending most of its time sitting here blocked, waiting on an external system, an external socket read 0. So whenever you see this kind of information in profiling data, that means that your system is waiting for a response from an external system. Now I know in this case that it is the legacy bank account system which is slowing us down at this point. So normally I would go and optimize that system, having optimized this one. However, in this case it's just a demo, and I can in fact optimize this system or make it way faster just by passing a different command line parameter into my legacy bank service system. It's not really necessarily a solution you could apply in production, but it's just an example of how you can find a blocking problem that's related to another service in your system, and then when we rerun the merge accounts benchmark, we are way faster at under 1 second. So in this demo, we looked at a couple of different things. We looked at how you could see a lock within a profiling view that we were able to optimize away as a problem by making it a more fine-grained locking strategy. And then I was also able to demonstrate an example where we could see waiting on an external service as a bottleneck in your system. If you want to take a look at these demos, they are on GitHub on the Opsian/performance problems example GitHub repository. Feel free to take a look and see how it goes with your own IDE and see what the code's doing there in more detail. If you're interested in a free trial of our Opsian profiler, which not only can help you solve problems in a development environment like this, but is also low enough overhead and reliably usable in an always-on production environment over a whole cluster of systems, then just go to opsian.com and sign up for a free trial now.